This is our first CITA seminar of the year. It's a pleasure to have with us David Hogg, speaking from NYU. So David got his, he was first an undergraduate here at the University of Stanford.
No, I was actually at MIT, but I worked here. I did my research here in the summer.
With Scott Tremaine at the time. Then he got his PhD from Caltech. He then moved to the Institute for Advanced Study, where he was a long-term member, and he then ended up at NYU. He works mostly on observational cosmology, using our own galaxy or other galaxies, using the SDSS. That has been his main focus of the last few years, and he's going to tell us today about how to integrate the Milky Way.
Great, thank you. Yeah, actually, when I was here as an undergrad, I was working with Tremaine, working on classical dynamics in the solar system, and I've come back around to that, strangely, through a strange path, which I'll say something about in the talk. So the summary of my talk is too long here, and there's too many view graphs, so I'm going to skip some things. But basically, I want to get across three general things. One is, there's a lot of ways for inferring. We want to infer the dynamics of objects from a snapshot of their current properties. And I'm motivated here by Gaia. So I'll talk about Gaia in a minute. But Gaia is going to take a billion stars and take some data on a billion stars and precise data on more than 10 to the 7. And we want to infer the potential or the dynamical state of the Milky Way, its accretion history and so on, from that snapshot. Is that even possible? So that's kind of where we're motivated. Like, how are we going to deal with that data set? And if you look at the Gaia team treats this as one of their top priorities, but actually doesn't have a worked out plan for how they're going to do this. So it's a very interesting and open area of research, and I encourage people to think about this problem. It's a big problem. So the methods for dynamical inference that exist right now are all designed for integrable phase-mixed dynamical systems. So if you think of Schwarzschild modeling, you've probably heard of Schwarzschild modeling, or the Oort limit, or virial estimators. Those are things that work on integrable phase-mixed systems. And I'll talk a little bit more about what I mean by that. In reality, in the Milky Way, the phases aren't mixed and the system isn't integral. So then I'm going to talk about what you do in the case when the phases aren't mixed and what do you do in the case when the potential isn't integrable. And I'm not going to answer the final question of how you deal in this situation. It's too hard. It's not a solved problem. But I will give some ideas about how you might proceed. Certainly there are ways in principle to proceed in this situation, but right now they're computationally intractable as far as I can tell. But we're interested in, my group is interested in performing inference that approximates what you'd like to do here, and it turns out to be a very interesting kind of intellectual set of problems there. Okay, I'm sure something does this. Control.
It's a function.
Function, page down. Come on, baby. I've broken your computer. Space, but that'll start it into its... Well, let me summarize again. Oh, there it goes, there it goes.
Good thing you put the summary first.
I know, you got to start with the summary. I learned that from John McCall. Okay. No. Okay, good. So my motivation is slightly different from most people who are thinking about these problems. My motivation really is about the properties of the dark matter. So there's a lot of different things to say about the dark matter, and I'm not going to say very much theoretically about the dark matter, but I want to just remind everybody that if the dark matter doesn't annihilate, then our only option is dynamics for imaging the dark matter. So if we want to image the dark matter rather than just get rough measurements of it, we're going to have to use dynamics. And we're going to have to use dynamics of some kind of structured things if we're going to see details of the dark matter, the details of the dark matter distribution. So if dark matter annihilation does happen and it is observed, and I think Finkbeiner is going to talk a bit about that here tomorrow, if dark matter annihilation is being observed, one question is, how do we confirm the detections? In fact, in general, a dark matter annihilation detection is hard to confirm dynamically. Imagine a substructure in the galaxy lights up. It might be annihilation. How do you confirm, figure out the mass, and so on? You're going to need to use dynamics. And then if you don't have an annihilation signal, the only way to see the structure in the dark sector is with dynamics. And we expect extremely rich structure in the dark sector. Everyone should remember, think of your dark matter simulations you've seen, bash, bash, bash. You expect incredibly rich structure. So there should be something there to observe. Oh, that hurt. I'm doing something very wrong. OK, I got it. I understand what I'm doing wrong. OK, so reminder, the Gaia mission. You might not have thought about this much. For some reason, this looms much larger in Europe than here in the US. But the Gaia mission is orders of magnitude. Oh, did I say that out loud?
Here in North America.
Actually, whenever I enter Canada, I travel on my US passport, and they always say, actually, you were born in Canada, so you don't have to use this passport. And I'm like, oh, I've repudiated my Canadian roots. And then I go into the little room, and I get cavity searched. This is going to change what we know about the galaxy by orders of magnitude. We're talking exceedingly precise. We're talking 1 billion stars. So this will be one of the largest astronomical catalogs created at all, and far more precise than anything that's come before. So it's just, if this does not tell us an enormous amount about the Milky Way, we should stop working on the Milky Way, because this is about it. Like, to do the next generation after this is really hard. So this is important. Either we figure out what the Milky Way is doing with this data set, or the whole study of the detailed properties of the Milky Way is a waste of time.
So how far out will you measure?
Of course, it depends on the luminosities of the stars, but roughly speaking, if I should draw a picture, but if here's the Milky Way disk, and here's us here, it's like a bubble here. It's an hourglass-shaped bubble that it measures. Why? Because it doesn't see as far in the disk. It's optical detectors. So it sees a short distance in the disk, and then it sees for a kiloparsec or two, or really, I mean, it gets some reasonable precision out to several kiloparsecs above and below the disk. But it is nowhere near a whole image of the Milky Way.
Okay, so it's actually fairly small radio.
It is. We're still only talking about, by volume, like 10% of the Milky Way. We're not talking about the huge fraction of the Milky Way. But we're talking about a lot of stuff.
There is this old story of thin and thick disks, which I now understand is more of a continuum. But
yes.
Does this actually break out of that, or
yes.
is this all?
Yeah. Like the giant stars will have excellent precision to very large distance in the halo. So there'll be a small fraction of the tracers that'll be measured.
Very far.
I think the brightest giants will be measured basically to 10 kiloparsecs. So there'll be some information to very large distance. It really depends on the brightness. It's all brightness, as you imagine.
The O stars do have 31, so we're going to do about now.
Yeah, so exactly. So we'll see, but for O stars. But of course, there's no O stars in our own halo, so that hurts. One of the interesting things about Gaia is it's optical, not infrared, which has some interesting impact on what it does. But I don't really want to talk about the specifics of Gaia, and as you can tell, I don't know all that much about the specifics of Gaia. I'm more interested in the general question is, will this data set transform our knowledge, and can we image the dark matter, which is kind of my interest. Yes. Okay, good. So just a reminder that when you run one of these missions last a few years. The orbital timescales in the galaxy are 10 to the 8 years, so you're not measuring the accelerations of the stars. You're only measuring their positions and velocities. You can say, duh, fine. But that's important because remember that now think back to high school, right? There's a force law, and there's initial conditions. Position and velocity are the initial conditions. And then there's a force law, and your orbit is determined by the force law and the initial conditions. Well, you can't figure out the force law by just measuring the initial conditions. Like all the stars in the galaxy, measure all the positions and velocities. Wait a few billion years, they'll all disperse. Like you don't know whether they're, you have to, obviously you're going to have to make additional assumptions. So that's the question. Now remember, how did Newton infer that it was 1 over r squared? Newton didn't have just the positions and velocities of the planets. In fact, he didn't have the positions and velocities of the planets. What he had was Kepler's understanding that the orbits were ellipses with the sun at one focus. And that, from that, he, or actually I should say Hooke, here, according to some people I should say Hooke, inferred that it was 1 over r squared from the shapes of the orbits. But we don't get the shapes of the orbits in general from Gaia unless we make additional assumptions. Okay, and now another reminder. This is now junior or third year, I guess, since I'm in Canada, physics.
Sorry, what about the rotation curve? Doesn't that give you the potential?
Only if you know that the orbits are circular.
They are this
How do you know that? I certainly don't know that. Actually, we're preparing a paper right now which suggests that there, right now in the Milky Way, there's quite a good evidence that there is no circular orbit in the Milky Way.
Well, they are in the mean. Yeah, with billion stars.
Good. One thing you can definitely measure in the galaxy is its mean mass within some radius. You can do that with just virial estimators. You can just apply the virial theorem to various populations, and you're going to get the mass roughly right. But I'm talking about imaging. If all we want to know is the mean mass, we already know it. Don't fly billions of dollars of metal to tell it to me. I already know it at the accuracy you can't. In fact, we know the circular velocity at the accuracy we can know it now. And in fact, with a student, I'm writing a paper now about the fact that there aren't actually closed circular orbits in the galaxy. We have pretty good evidence that there's no closed circular orbits in the disk, and from the substructure in the disk. And that means that you can't know the mean mass, and all you can know is the mean mass at only to 1%-ish accuracy, and we already know that. And so if that's all Gaia is going to tell us, we already know it. So we're talking about imaging the detailed structure of the galaxy. That's my interest. Okay. If all you want to know is the mean mass, you're done. You can leave now and get back to your email. Okay, integrability. So now third-year mechanics. There are symmetry. If you have an integrable potential, then you have symmetries that lead to 3 conserved quantities. In 3 dimensions, there's 3 conserved quantities. And the standard thing is to talk about action and angles. There's 3 actions, which are the 3 conserved quantities. And there's 3 angles, which are the conjugate momenta, or conjugate coordinates to these momenta. And the actions are invariant, and the angles increase linearly with time. And so any orbit fills a 3 torus, because any test particle on an orbit in an integrable system is moving linearly in time through 3 orthogonal angles, and so it's filling some 3 torus. And except for resonance situations, which are irrelevant for us right now. They might come back. Integrable systems are great because there's a lot of things you can do with them, and they're infinitesimally rare, as you know. Right, that's the whole discovery of chaos and all that from Poincaré on. Okay, so how does dynamical inference occur up till now? So if you look at any estimator, right now, as far as I know, any estimator that people use to estimate the mass of something assumes not just integrability, but also mixed angles. So there are virial estimators. And virial estimators is where you assume the kinetic energy is about the same as the potential energy. That's a mixed angle assumption. That's assuming that the orbit has gone on for long enough, or the orbits of all the stars have gone on for long enough that they've explored their range in kinetic energy and potential energy, and on average they'll be about the same. And so the idea of a mixed angle system is if you're integrable and you have these angles, the particles all pass through their angles at different rates. And so if you put a bunch of test particles out onto the orbits and wait many dynamical times as they orbit, eventually they will be randomly distributed on their 3 tori. So you start with whatever you start with. If you wait long enough, as long as your system isn't resonant, you'll just fill the 3 tori democratically. Kind of obvious. And the nice thing is, if you have this property, then your distribution in phase space, in the 6-dimensional phase space, will be a function of the actions only, and there'll be a symmetry in the angle direction. Everything will be symmetric in the angle direction. And that is the fundamental assumption of all the current methods for doing dynamics. So for instance, Schwarzschild and Oort, in the other order, both proposed methods for understanding aspects of the mass distribution in the galaxy, and they both assume that it's integrable and that it's mixed. So you measure all the positions and velocities you can, and then you loop over all integrable potentials, and you compute all the actions, and you ask whether a set of angle mixed populations generates the distribution of stars that you have, and that whether that also whether you can populate that set of orbits and create your potential. So you have to create your potential out of particles that are on these phase mixed orbits, and you have to generate your observed stellar distribution by orbits that are on these potentials, and you try and solve that whole problem.
So the dynamics of the galaxy rather than the statics of the galaxy, because it's always dynamical.
Yes.
Does that mean that that mixing is essentially perfect because of the dynamical action?
No, it's just the opposite. All the action that's happening prevents you from ever getting mixed. So I'm going to come back to that. Basically,
right.
It's not mixed. It's not integrable, and it's not mixed. You're dead.
And,
all of these assumptions are wrong.
Is that well calculable with current and body codes?
No. No. But I'll talk a little bit about just some order of magnitude stuff. But yeah, if you just want to know roughly the mass, 10% measure of the mass, you're fine, because these kinds of measures are not thrown off very much by outliers and stuff. So it's not too bad that you're not perfectly mixed. You get an okay measurement. But if you want to do precise things like learn about the most recent accretion event or find substructure, this is all going to be wrong. Okay, fine. Good. So we assigned ourselves an absolutely trivial problem, because we figured if we couldn't solve the most trivial possible problem, we're dead. So here's the most trivial possible problem. Newton figured out the force law was 1 over r squared by looking at the ellipses, right? By figuring out what force law produced the ellipse with the sun at one focus. We have asked the question, can we determine that the force law is 1 over r squared by just looking at a snapshot of the positions and velocities of the planets? So we're just going to take, at a single moment of time, what are the positions and velocities of the planets, and ask, from those positions and velocities alone, can we determine the mass of the sun and the force law goes like 1 over r squared? Now, it says here, of course you can, but everyone should be thinking, of course you can't, because the force law is the force law, and x and v are the initial conditions, and you can have any initial conditions in any force law. But you have to make additional assumptions. But there's an assumption that's very good that you can make for the solar system that's extremely good, which is that it's dynamically old. So if the solar system is dynamically old, then the planets will be at random points and not resonant. You have to assume it's dynamically old and not resonant. Then the planets will be at random phases. Yeah.
I thought Hogg, originally, was the guy that came up with the 1 over r squared just from Kepler's law. It's a
Yes.
typical notion. So you just take Kepler's law and assume things are moving on circular orbits. Then it just falls out naturally.
Yes. I'm not sure actually how Hooke did it. So one interesting thing is,
But Kepler's law.
So right.
It means you already know something about the dynamics.
If you're thinking of a squared goes like t cubed, so that law requires that you have seen the planets go through an orbit.
Plus v goes as r as well.
That's going to be highly relevant. So hold on to that thought. That thought will be very relevant. The fact that it's v, exactly, it's right, good. So hold that for a second. That's going to matter. One interesting thing is you can derive this just from dimensional analysis. If you have Kepler's law and dimensional analysis, you get that. But there's no evidence, as far as I know, in the historical record that they used dimensional analysis. Hooke did a bunch of math to determine it. He did not, or Newton.
Read the biography of Hooke. It's
Yeah.
written by her.
Yeah.
That's exactly what she discusses. That was the discussion that was going on
Yes.
in certain scientific circles.
Certainly, yeah. But they were definitely using the periods where you have to see an orbit pass.
And Powell's challenge to Newton was, can you show that law actually makes ellipses?
Also makes the ellipses. Right.
That's the historical.
Good. Thank you. That's good. That's a good point. The reason why you can do this is the solar system is old. And so imagine, let's say we just tried to determine the mass of the sun. So forget about the force law for a second. So imagine you just want to know the mass of the sun. And all you have are the positions and the velocities of the planets right now. So like right now you're given the positions and velocities. And now you can dial the mass of the sun. If you dial the mass of the sun very low, then you find that all the planets just happen to be right at perihelion. And they're flying way out on orbits like this, and they're going to come back to perihelion sometime far in the future. And if you dial the mass of the sun too high, you find they're all at aphelion, and they're just plunging in. They're about to plunge in yet again into the sun. If you dial it too high, they'll plunge right into the sun. Right? So you can see that there's a happy medium where if you go low enough, if you go too low, they're all at perihelion. If you go too high, they're all at aphelion. And there's somewhere in between where they're at mixed positions. And so you can see that you can actually determine that. And then you can determine 1 over r squared, because as you change the slope of the force law, you get them, the outer ones at aphelion, the inner ones at perihelion, or you get the other way around. You can see you'll get correlations between phase and position that are clearly not consistent with it being an old system. So you can see that, of course, you can do this. And there's a very nice paper by Belavarov and Levin that's called Orbital Roulette that implements this thinking about the galactic center. And I'm not going to say much more about that paper, except that it's very nice, and it was the inspiration for us thinking about some of these things. And of course, in the virial theorem, you're doing the same thing. The virial theorem is basically doing the same thing. You're saying that if the system is old, the average kinetic energy ought to be related to the average potential energy. Everyone know that? So you can just do this problem in the solar system with the virial theorem. You can just find the mass of the sun that makes the kinetic energy equal to minus 1/2 the potential energy. And the virial theorem, the virial method, by the way, is amazing. It's so amazing. It's a completely simple method. It's got very little like mathematics behind it, and yet it works trivially with missing data, which actually doesn't work for any other method until the ones that we're working on. It doesn't work on any other of the sort of published methods. And here's this orbital roulette, which I'm not going to talk about too much. But the idea here is you define these angles in the action angle formula. You find these angles, you define the angles, you measure the angles, and then you change the parameters and look at the angle distribution, and you try and find the parameter settings that make your angle distribution look random. And then you have your parameters of your potential. So that's kind of the... and I call it frequentist orbital roulette to slam it a little bit because, in fact, it involves an ad hoc choice of an estimator. It's not an optimal thing to do in the system. It's just a choice that you can do, but it works very well. So I'm not objecting to it, but it's very hard to use with missing data. So it doesn't know how to deal with missing data. In most data sets, including Gaia, you will not have all of these 6 dimensions measured equally well. You will always have significant measurement uncertainties which blur what you can understand about the angles. And there's usually selection effects, and it's hard in these kinds of frequentist estimator kind of setups to include those effects. And that's one of the things which is pushing us towards forward modeling the data. So, okay, so what we're doing is we're trying to make systems that work that are essentially Bayesian, but ones where you forward model the data and then work out your parameters based on modeling your data. And we're generalizing the Kepler problem and the Oort problem. And this is stuff I'm working on with various people, including Ian Murray, who's in computer science here, who is an extremely good inference person. He's in computer science, but he's very much a scientific Bayesian. So he's been very helpful to us, and I'm back working with Tremaine again. Okay. Okay, good. So I'm just going to talk about the specific example of the solar system. So what we did is we took the 8-planet ephemeris. There's now 8 planets, I'm told. That's different from when I worked on the solar system. There were 9 planets back then. And we took a snapshot of the positions and velocities on 2009, April 1st. And we did that because we thought of this project as kind of a joke. And then we spent months and months of incredibly hard work on this joke. And now we understand this problem is much more complicated than we thought. We assume that the acceleration in the solar system is amplitude times r over r naught to the alpha, or to the minus alpha. So we're assuming a spherical potential that's a power law. So we're assuming the simplest thing you can possibly assume. And just asking, can we infer these two parameters? So we're asking. And we are modeling the distribution function as being a distribution in the binding energy and the eccentricity. We use weird units. We use the ln of the binding energy and the eccentricity, so we have to use a Jacobian to connect it to the distribution function, and we apply Bayes' theorem. So that's what we're doing, and we're asking, can we figure it out? So here we go. So this shows you the orbital phases. So we've
What was your prior for Bayes' theorem?
I'll show you that in a minute. So the inputs to this are going to be, we are looking at what happens in the frequentist situation is you're looking at the phases. So you're looking at the phases of the planet. So we defined a phase which is 0 at perihelion and pi at aphelion and goes around. That's the phase of the planet as it goes around. And then these, you can't read these plots, but this is alpha on this and A on this. So this is the power law, and this is the amplitude. And this is the phase as a function of these properties for Mercury, for Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. And you can see interesting things here. One is, in general, the phase goes from one end to the other end as you change the mass. Because if you make the mass too low, Mercury is at perihelion, and if you make the mass too large, it's at aphelion. So you see they all have that property that they're white on the bottom and black on the top. That's because the phase is varying. And then you'll notice that there's tilts, that the inner planets tilt this way, Earth is flat, the outer planets tilt this way. That's because the R naught we're using is 1 AU. So there's inner planets are different from outer planets in this. And then you'll notice that some of these are very smoothly go from one phase to the other, and some go very sharp. So what's the difference between Mercury and Venus? Such that Mercury very smoothly changes its phase as you change the parameters, and Venus changes the phase really quickly. Eccentricity, right? Venus's eccentricity is very nearly 0, which means its velocity vector is perpendicular to its radius vector, very close to perpendicular. So it's either on an exactly circular orbit, or it's exactly at perihelion, or it's exactly at aphelion. See? Venus is a very constraining object because its velocity vector is very close to perpendicular to its radius vector. So it is very constraining. For a very large fraction of models, it has to be right at perihelion. And for another large set of models, it has to be right at aphelion. And it transitions very quickly. So,
Very circular too, isn't it?
say again?
I just remember wrong.
Which?
Jupiter, I thought, was at least as circular as Venus.
No, well, not according to this, but it depends a little bit. Depends a little bit on April 1st. So it depends on what the angle was on 2009 April 1st, of course. So it's really that angle, that momentary angle, that sets it. So some of these are doing better than they should, and some doing worse than they should.
Neptune's got as long as Jupiter's is the same.
Okay, so you can see this shows you that this is going to work pretty well. But that's just very qualitative. Here's our Jacobian. This is the Jacobian in that transformation I'm showing, but basically this is showing you the sensitivity of the phase. This is the sensitivity of the phase to the parameters. And you can see the high sensitivity to phase in Venus and Uranus. Very, very constraining. And you can imagine if I just multiplied this function by this function, I would get a point right at the center, which would be very close to the right answer. But of course, what we in fact do is we put priors down. And Dick asked about the priors. We just put a flat prior on this exponent. We put a flat prior on the log of the mass, just for demonstration purposes. And then we create a posterior probability distribution function using a distribution function model, and we have to model the distribution function in energy and eccentricity, and then we have to marginalize over the parameters of the distribution function model. So So it's pretty brutal. All we want to know is the mass and but we have to model the distribution function, find the best distribution function, marginalize over the properties of the distribution function, and then produce our dynamical parameters after that marginalization. Because our model for the system includes the mass and the exponent, but it also includes the parameters of our distribution function. And we don't care about those. They're nuisance parameters. And this is going to be the key problem with any method in which you infer dynamics. You spend all of your time inferring the distribution function, and all you care about is the dynamical parameters. But that's what happens. And oh, by the way, here's the answer. This is the exponent alpha, and we marginalize over the distribution function models and over this over our whole space in the mass and in distribution function parameters. And we get a peak that does happen to include, I think this is the 95% confidence interval, this dark gray bars. It does include 2, alpha equals 2. And this is, if you believe our priors, which you shouldn't, this is a posterior distribution function, probability distribution function for the exponent in the force law. So we were able to determine that it's 2. And fundamentally, it's because the velocity goes like 1 over the radius. OK. Here, by the way, is the virial theorem. So if remember we had the virial theorem. In the virial theorem, you can write down what relationship the kinetic energy should have to the potential energy as a function of this exponent alpha. It's like 1 minus alpha should be the relationship between the potential energy and the kinetic energy. And when you plot those lines, they all basically cross at a point. Basically, if you go out here, if you go in this direction, some of them have too much kinetic energy and some have too much potential energy, and over here it goes the other way around, and they all basically cross at a point. And then there's a region here that's unbound, where at least one of the planets is unbound. This region is where at least one planet is unbound, and this region is where at least one planet falls into the sun. And there's some pretty extreme models here. Alpha equals 5. That's a model. At alpha equals 5, every trajectory goes through the center of the sun. It's pretty bad.
You're a bit lucky here that the sun has circular orbits, then, given that these spaces.
Good. Good. So this is what we learned. So what we learned was, so one thing you can ask, there's a bunch of things you should ask. So I was very happy that this came out so well. We're within a few percent. You see, we measure alpha to a few percent. But the ephemeris values, the ephemeris we were using to compute x and v is good to 8 digits of accuracy or 13 digits of accuracy for some planets and 8 for others or whatever. It's good to amazing accuracy. Did we measure this to 8 digits of accuracy? No. So the first question is, where did that accuracy go? Why did we do so badly? And the reason is, where it went into modeling the distribution function. But as you point out, why did we do so well? You can ask, why did we do so badly, which I just asked, but you can ask, why did we do so well? The reason we did so well is that, in fact, the planets are close to circular orbits. And that means when we model the distribution function and marginalize over the distribution function parameters, that marginalization is still very peaked around a set of small eccentricities. So the eccentricity distribution is narrow. That permits us to grab onto the dynamical model. If we had eccentricities all over the place, we would have done much worse. In fact, with 8 planets, if it was randomly distributed eccentricities, we wouldn't have been able to determine it.
With 8 planets, it wouldn't work.
Wouldn't have worked, yeah.
Those three error bars with the number of objects you have. If you have more planets, I guess it'll do a better job.
Yes, with more planets, you'll do better, provided they are drawn from the same eccentricity distribution. So if you add more planets, but draw them from a broader eccentricity distribution, they can even make the answer worse. So if God could tell you, these planets have low eccentricity, you will do better than if you use them all. And in fact, I just screwed up there. And in fact, if here, these 2 planets alone do better than all of them combined. Right?
So what would the moon do?
You mean if I thrown in the moon as well?
It would probably say, I have no idea what.
Good question. I mean, one of the interesting things here is we treated the planets as test particles, of course. And of course, the larger project is to actually determine non-trivial aspects of the potential. So we should throw in all the satellites and ask whether we can determine which of the planets have mass from the snapshot. Because that is very like the substructure problem. Can we find the substructure in the system? So in principle, you should be able to see the substructure, i.e. if you threw in all the bodies, put in all the minor bodies, you should be able to see that Jupiter has mass because it's shepherding a bunch of stuff. You should be able to see that, Earth has mass because it's got a satellite. You should be able to see all those things. But yeah, it would be, right. But you can see why it's starting to look pessimistic for determining the properties of the galaxy. Okay, even though we did a good job on that. Okay, but as I said I would tell you, the angles are never mixed. The Milky Way has only been around for 10 to the 2 dynamical times. Stars are formed in groups with like a few kilometers a second in size, but the orbits in the Milky Way are like 200 kilometers a second. So it takes many more than 10 to the 2 dynamical times for the Milky Way to become angle mixed. So the Milky Way just can't be angle mixed from a pure theory point of view.
What about violent relaxation?
You can hope for violent relaxation, but if you look at any part of the Milky Way in detail, you find phase-space structure.
Yeah, but that does, but violent relaxation does like 90% of the work.
You can hope that violent relaxation certainly helps you, but there are stars, new stars forming all the time that haven't been subjected to it. Basically, you can't assume that you have. And certainly that violent relaxation, though it will mix the angles a lot, it won't produce a distribution function that is a cross product of a distribution in actions times flat in the phases. It won't produce that. It might produce something that's mixed, but it won't be mixed uniformly on 3 tori. Because that requires the grinding of the cyclical churn. Okay, so now I'm going to assume integrable potential but unmixed phases. And I said theoretically they can't be, the angles can't be mixed, but also observationally. If you notice, the Milky Way is filled with, there's all these satellites flying around, there's tidal streams, there's velocity structure in the disk. You can just see it, just observationally. So to forget about theory, it's just observationally not angle mixed. So one famous cold stream. Here is the Grillmeyer and Dionatis stream. In fact, Ray, I think, just wrote a paper on the cold streams, which I'll comment on in a minute. So this is, I don't know if you can see this here. You might have to have observer's eyes, and you guys, you theorists maybe can't see this stream here. But anyway, this is a very cold stream of stars, very cold in the sense that it has no measurable velocity width. It's very thin on the sky as well in angle. And it's believed to be the tidal tail of a disrupting object, although we haven't found that disrupting object. And if it is the tidal tail from a disrupting object, this stream comes close to tracing out an orbit in the Milky Way. So this is an interesting kind of object because this is not a phase-mixed object, right? This does not fill a 3 torus in the galaxy. This is just a line. But it's a very cold, a very, you might say, a very coherent structure. And so this coherent structure could, in principle, tell us things about the potential of the galaxy. And that's an interesting idea because now, if we don't have phase mixing to count on, and besides which I kind of argued that phase mixing isn't that useful, if we want to do precise things, maybe we need to find coherent structures. So the thing we've done with the Grillmeyer stream, just as a baby step towards this, is assume that the stars on this stream lie on orbits very close to the original satellite orbit, so that they basically trace out an orbit. And then we ask, can we determine the properties of that orbit? If we can determine the properties of that orbit, then we are actually seeing a test particle orbit through the galaxy. And a test particle orbit through the galaxy, there it is. You actually measure the acceleration vector. If you have an orbit like this, you can measure the acceleration vector all along that orbit. So that would be a way to do a precise measurement. And of course, I'm telling you this because we have succeeded. I'm not going to tell you about the properties of cold streams. And this is the paper. We just put it on archive maybe a month ago. And Kopasov is a graduate student of Rix's at Heidelberg who's just finishing now and off to Cambridge. Extremely good guy. So that's just another representation of it. I don't care about that. So now the problem with this stream is that stream, you saw it, it stood out like anything in that first figure I showed you. But in fact, it's a very subtle thing in the data. So here's a distribution of stars that have been selected to have the right colors to be in the stream, and a cut through, and you see the base level here is 400, and here's the stream, a tiny little blip over 400. That means there's no star on the sky for which we can confidently say it's a member of the stream. Right? For every star, all we can say is it's got these stars in here have a slightly higher probability of being in the stream than these stars out here. See? So we only have probabilistic information. But it turns out even with only probabilistic information, you can still figure out a lot about the stream because we heart statistics. Let me skip that and just show you this. You can't read any of these axes. We can work out the distance to the stream. This is an angle along the stream. We can work out these red points are the distance to the stream measured in bins. And how do we measure the distance? By looking at color magnitude diagrams, but again, only statistical ones because we don't know any individual star. So we're just doing foreground-background modeling to get the distribution function in color magnitude, and then we can fit the distance from that. We can get transverse velocities. These are proper motion-based transverse velocities. Not only does each star have no strong probability of being in or out of the stream, but each has a very bad measurement of its proper motion, like a 1 sigma proper motion. But there's hundreds of stars in the stream, so we can combine the proper motion distributions. We can difference on-stream and off-stream proper motion distributions, although actually we model it. But you could difference them, and then you see. And so we can measure the transverse velocity of the stream this is the transverse component, and this is the longitudinal component of the proper motion. And we can measure the radial velocity, and the way we measure the radial velocity is the same thing. We took radial velocities of a large number of stars and then did foreground-background rejection on those stars. So what is this? This may not seem all that impressive, but this is a 6-dimensional map of the stream. This is the angular shape of the stream. This is the radial shape of the stream. This is the transverse kinematic shape of the stream. And this is the radial kinematic shape of the stream. So we actually have a 6-dimensional map of this stream. In fact, I think it's one of the few things in the galaxy for which we know all 6 dimensions of phase space. There are some globular cluster claims, but don't believe the hype. So there's only a few objects. There's a few globular clusters and this stream where there's 60 information. But with this, there's not just 60 information, but it's along the length of the stream. So because we have velocity, for instance, along the stream, we have an acceleration. So we can measure the acceleration, the 3-dimensional acceleration of the stream. By the way, these lines going through here are models in different potentials. And so we've done things like model the potential of the galaxy, and you can read the details in the paper. And basically we find that when you model, this is the mass of the disk of the galaxy, and this is the oblateness of the halo of the galaxy. And basically a perfectly spherical halo and a 10 to the 11 solar mass disk fits the observations perfectly. So it's a little bit disappointing that the orbit is really well fit by exactly what you would have guessed before we started. But if the Milky Way doesn't contain just one cold stream, but as Ray and I hope, contains thousands of cold streams, then you can build up an acceleration map all over the Milky Way, in principle, by doing this kind of 6-dimensional modeling of the stream. Build an acceleration map that turns into a map of where the mass is. So that is kind of the hope, and I'm just going to, oh, by the way, this is what the stream looks like in 3D. There's the galaxy. This is our position in the galaxy. It's over our heads, and it's going around. And it's one of the reasons we were able to measure at 6D so accurately is it's counter-rotating. If the Milky Way is rotating this way, it's coming across that way. So it's counter-rotating with respect to us, and that means we get it at higher signal-to-noise than we would if it was going at a random direction. So it's a fortuitous case.
So if you had some really interesting dark matter clamp which was deflecting that stream, wouldn't that then go at a velocity which would actually destroy it if you couldn't see it anymore?
Good. I'm about to talk about that. In my almost no time. So, okay, so I've said all of this, that if the stream is cold, And it really does trace out an orbit. And the question of whether it traces out an orbit is really interesting. I'm not going to talk about it, but I'm thinking about that problem a lot. Then the stream can be used to kind of directly measure the acceleration vector under assumptions, as always. I'm not going to go through all that, but I have to say this. Tremaine has a very good idea, which if somebody wants to do this, it's just so clever. Generically, stars are born in small groups, and those groups are disrupted tidally. That's generic. So that means the Milky Way should be filled with 2-star streams. Basically, for every star, there should be other stars, which if you run back the clock, come back to the same place. That's a really strong constraint on the dynamics of the galaxy. Somebody should work that out. It's time, right? It's time evolving, so probably, yeah. But I'm going to come back to the very end. So let me say the last thing, which I'll just end with the craziest craziness. So first of all, the potentials are never integrable. You know that the Milky Way is not going to be integrable. It's got to be chaotic. Even the solar system is chaotic, so the Milky Way is definitely chaotic. So you have no time independence. You have no axisymmetry. There will be no symmetries. And we can even see in the disk now that axisymmetry is not correct. So we know that and you know from the satellites and the bar that there isn't time independence. Pattern speed is unlikely to be fixed, etc. There's none of these. Even the basic things aren't held. Even the basic symmetries aren't held, let alone more complex symmetries which guarantee integrability. So there's definitely not integrable. There's no way. So what do you do? So one thing you can do, and this is something that, and I'm just going to say a few. Now I'm just talking out of my ass because I don't have anything. Oh, did that go on the web? Because I don't have anything very specific to say about this yet, because I'm still thinking about it. This is something that Ray just wrote a paper about, which is that the streams, because they're cold, coherent objects, they're very sensitive to details of the potential. So a stream which is starting out on an orbit, if it gets perturbed by some time dependence or some concentration, that perturbation will grow with time. It will send part of the stream slightly off its orbit and it will grow. And in general, you expect these cold streams to have kinks in them. And this is a random sampling of kinks you would expect. This is just a perturbation theory calculation. And you can see all sorts of generic things, including these little folds. And actually, all of those things are visible in Ray's paper from a few days ago. And Ray is asking the question, can you use the statistics of these to constrain the abundance of substructure in the galaxy? And they look very constraining to us as well. However, you can also ask them, can you use them to identify individual actual substructures? You can ask the question, can I see a substructure flying through the galaxy? Because that substructure, as it flies through the galaxy, is passing by all these streams, perturbing them. Those streams travel on, the perturbations grow. So this substructure should be flying through the galaxy, leaving behind a wake of perturbations to cold streams. And you should be able to, in some sense, image this substructure by finding a model that explains all the perturbations. So we're thinking about that question. Can you reconstruct specific perturbers from these objects? There is one stream perturbation of this form that is known, and it's debatable, I have to say, but in Palomar 5, the tip of the Palomar 5 tidal stream has a little divot in it that looks very much like this one. Right there.
But because there are so many perturbers, there must be some estimate for the lifetime of one of these
streams. Yeah, well, one of there's so many interesting things in this area. Like one of the interesting things is that cold stream by Glomar and Dionysus was found partly because it is very cold and very thin. If it had been beaten up by substructure, they might not have detected it in the first place. So it might be that there are lots of streams that got beaten up by the substructure, and that one just happens to be an incredibly lucky stream that's escaped the constraints. So that's an interesting question. I don't think that... It's also nearby. It's not out in the worst part of the substructure by any means. Exactly. Right. Right, so working out in detail what the constraints are from any one stream is quite complicated because you have to think about selection issues, and then you have to think about what these individual streams are really sampling.
Small radius, though, right?
All the ones that are known so far, but that's just because of limits to the data. We couldn't have detected this one further out. Say again?
But to be finally disrupted, right? Radius has to be small, right?
Well, it depends on the properties of the progenitor that was disrupted. But stars form in small groups. Stars form in cold groups. So there will be cold stream. There will be cold substructure everywhere.
So M31 news streams pretty far out. And of course, the orbit is roughly parabolic, so it might get disrupted if the
Yes.
part of the orbit. But then the stream comes fully out to spend most of its life.
Even this Grillmeyer Dionatus stream actually goes to much larger radius than where we're detecting it. We're detecting it here near pericenter, but it goes out to something like 50 kiloparsecs. So even it is seeing a significant fraction of the...
So what's the progenitor? Is it a silent galaxy?
Nobody knows. People are all arguing about this. This is consistent with being a globular cluster, a puffy globular cluster, or a tiny satellite galaxy.
All right, that's your thing why stars form because it's not silent.
So first of all, there's a generic statement that stars form in small groups. I don't know any evidence against that. And then second of all, if you just look at the halo formation process that's happening now, there's tidal disruption going on. Okay, and so I just want to say one last thing. So I said this thing that it's possible that we might be able to use cold coherent objects to image the substructure. And I think we will have tons of streams. Because SDSS, there's a handful of cold streams have been found, and it's a 2.5D map. Right? We barely have distance information in Sloan. Gaia will be a 5.5D map. So structures that are barely significant here will be whopping here. The Grillmeyer stream, things that are thousands of times smaller in mass than the Grillmeyer stream will be visible here. So if there's a 1 over mass squared number density of these objects, there will be thousands of streams once Gaia takes data. Streams with 10 stars will be easy to detect in Gaia. So it really will be a very different world when we have Gaia.
What are the statistics that you use to identify that you've got such a correlated structure?
It's complicated. You have to, in principle, to find these things, you have to loop over potentials. So this is why it's interesting. This structure will exist. Some of it will be easy to find, some will be hard to find. It depends on the complexity of the potential. If the potential is simple, you'll find them easily. If it's hard, if it's complex, you'll have to marginalize over potentials to find them. But of course, if these streams really do exist, in fact, this suggests a whole way of doing inference to determine the galaxy's potential.
So instead of doing pattern recognition in the 5.5D, you're actually going to say I've got to have a dynamical hypothesis?
Well, the first thing you'll do, obviously, is you'll do pattern recognition in the 5.5D. But then as you try and extend the stream and ask, are these stars out here part of the stream, you'll have to start making assumptions about the potential. And those will end up being measurements of the potential. They'll start out as assumptions about the potential, but they'll end up being measurements of the potential. Either that or you don't believe the Reverend. The Reverend Bayes. What was that? Exactly. There's additional information from metallicity and from colors. Where was I going to say? Yes. So in absolute general, now truly crazy, this is off the deep end. Stars form in cold clumps in phase space, as I keep saying, and everyone's rolling their eyes. Coeval stars have similar chemical similarities. The Milky Way formed by gravitational collapse from a homogeneous neighborhood. Marginalize over initial conditions, produce the observed data. Right? What are the parameters of the cosmological model? Assuming you guys figure out what the universe is made of, then all that's left is the phases of the local initial conditions that produce the Milky Way we see. And if you're laughing, it means you're understanding that this is almost impossible. It's impossible to imagine doing this. This is running forward models that include star formation and chemical abundances and matching star for star what we see now. Okay? That's impossible. But I bet there are approximations to this that are possible. And those, notice that if you do this and marginalize over these initial conditions, producing the observed galaxy, you get the marginalized accretion history, you get the marginalized mass distribution, you get marginalized probability distributions for all the nearby substructures. You understand the missing satellite problem. Well, by that point, the missing satellite problem will be like, oh, my great-grandfather David Hogg worked on that. Okay, it's not going to be easy, but if you are truly a Bayesian, you have to take your model and generate your data. Okay, I'm done. Thank you.
So the point at the end is something I wanted to ask you about anyway, which is that there have been attempts of various sorts to map back from galaxy observations to supposedly initial conditions from which things arose. And of course, the phase mixing is the complication which occurs, but with some smoothing assumptions and Bayesian assumptions, there have been some attempts. So it's obviously somewhat related to this.
Absolutely,
much
yeah.
cruder,
Yeah.
with much less information. Could you comment on this technique?
So, first of all, a philosophical point that I like to make is that right now, cosmology, there's the model, the Lambda CDM model says that the phases, on large scales, the phases don't matter. You just have to know the amplitudes. All the information is in the amplitudes. Okay? But in fact, we're actually observing an actual finite Hubble volume. And in my lifetime, we will know some information about the amplitude of every mode inside the horizon. That is not technologically unfeasible. By the end of SDSS 3, we'll already know some big chunk of the universe, 10% or close to 10% of the universe will have some measurement of a large number of modes inside the horizon. There's a finite number of modes inside the horizon. Some fraction of the cosmological world should be working on running initial conditions that generate the actual observations we have. There is a universe that we live in. We should be simulating not just the ensemble of all universes that have the same statistical initial conditions. We should also be simulating the set of universes that have our initial conditions. That's an important project. Just like we're living in the Milky Way. We could just say, well, it's just one of a bunch of galaxies. We should just study that bunch of galaxies and we can measure some rough properties and that's it. But we all understand that it's important to understand the detailed properties of our galaxy. It's also important to understand the detailed properties of our universe, not just statistical realizations of similar universes. So first of all, I want to say that I think it's a really important line of research. It should be done. That said, and in part because there aren't huge resources being put into it, none of the work in that area is anywhere near the level that we need to even start asking these questions. So nobody's thinking about the combination of speed and resolution. Nobody's been imagining the combination of speed and resolution you would need to talk about these. Now, there are current simulations that kind of have the resolution for this, but every galaxy takes ages. Like there are some simulations that are high enough resolution that you can start to ask some questions, like produce a disk like our disk and produce a bulge like our bulge. But nobody's thinking about marginalizing over initial conditions. That's not even close to true. So I would say the work that's been done in that area is excellent, and it's down the right path, and I think it's going to be a very productive line of research. For instance, if we had a chain of realizations that produced our actual universe, that chain of realizations could be used to design new experiments. So right now, when we design an experiment, we just decide, what size, volume, and how many galaxies we're going to measure. But we could be making much more detailed predictions about what we will see in those observations and which kinds of observations will be constraining if we had chains of realizations that produce our actual universe. Because each new observation would basically slice out a chunk of the chain and destroy it, and we'd have to build a new set of realizations. And so you can imagine it would create a whole new environment in which we could actually make observational decisions objectively, whereas now it's very subjective. So I think it's very important for the health of the field that we start doing that. That is not a comment on the technical properties of those papers, which they're good, but we need to go a long way to get to here.
Any other question? No? Okay. If not, let's thank David again.